Chapter 3. Welcome. Chapter 3 Physical Geography. Still talking about the atmosphere, but now we're going to switch our focus a little bit. We've talked about what the atmosphere is made of, the structure of it, and what is in it. Now let's talk about water and how water interacts in the atmosphere. Beginning with, let's talk about something we all know, Lake Michigan. So, when this book was published in about 2014, the Great Lakes from 1986 to 2014 had been dropping. Every year they're a little bit lower. As you can see this picture right here, the water may have been here one year and then down. And this was a serious concern. One thing is, uh, as the lake drops, it made it harder for ships to carry cargo. Because if the shallower the water, the less cargo a ship could hold. And a lot of goods are shipped through the Great Lakes, which would make it more expensive. And what was causing this drop in the water? The best theory was that we had had a series of very hot and dry summers and warm winters. And what happens is, if you have a warm winter, ice does not cover the entire Lake Michigan. It doesn't freeze over. And that allows evaporation to happen not only in the warm summer, but also in the winter. And evaporation is how the water leaves Lake Michigan. Rain falls, fills it up, and then water evaporates. So, our climates have been getting slightly warmer. We thought increased evaporation, this was going to be a new trend. But what's interesting is since this book has been published in 2015, we've actually seen lake levels come back. And in fact, if you look at the trend right here, here was the record lake level was in 86. It had dropped and dropped and dropped, and then since about the year 2000, really remained low. This blue line, by the way, is the level of the lake. This red line is the average height. You can see that we were below average for basically from the year 2000 all the way through to 2014. So 14 years of below average lake levels. Something happened in 2015. You can see right here that the lake began to rise again. And today, we are actually almost at record levels. Let's zoom in on that. Look at that. The average lake level, and this is based on taking measurements every day for the past 100 and some odd years, is about 578 feet. I'll show you the details in a moment. But we have been above record or above average lake levels ever since. And if you look at the trend, it's definitely on the upswing. So, the average height of Lake Michigan. Basically, if you measure the surface of Lake Michigan, it's on average over the last 100 years 577.5 feet above sea level. As of today, it is 582 and some odd change feet. In other words, we are 4.5 feet over normal. The record high, the highest we've ever measured was in 86, and it was 583 inches. And if you look at that, we're only about roughly a foot below the record high. So definitely something to think about when you go down the lakefront, when we do have the ability to go down again. Right? If any of you have been down to the lakefront in the last few years, you might see things like this, where the lake has overflowed the edges of the harbors or the beaches. I know if you go down North Avenue Beach, it's almost completely gone. So these record lake levels have been dropping. One of the things we see, the deeper the lake gets, the less beach there is. So this is North Avenue Beach off of Lakeshore Drive, and this white line is where the beach lakefront was approximately 5 years ago. So you can see in the last 5 years, this whole area used to be dry sand right here. It's all been submerged. One of the bigger concerns, though, is increased erosion. As the water gets deeper and covers more of the beaches, it also allows waves during storms to break further inland. This winter we had a huge storm that destroyed large sections of the lakefront path. It basically broke up the concrete and tore it up. So we're seeing this huge issue. And why? Well, one of the things we'll talk about, not this chapter, but down the road, is the polar vortex. Those are those cold snaps we've been having every couple winters now, where we have a day that doesn't go above negative 11 degrees. And when you have a very cold winter like that, it allows more ice to form and covering the lakes, which limits evaporation. The other thing is wet springs. So this May was the wettest May since we've been keeping records, about 120 years. It rained 20 of the 31 days. The second wettest May was last year, and the third wettest May was 2 years ago. So there's been this trend of very wet springs. And what happens is when it rains, it keeps the temperature a little cooler. So cooler maize with more water leads to less evaporation. So both a colder winter and a wet spring, even though we have maybe warmer summers, is making the water evaporate at a slower rate. So that is one of the things that we will be talking about in this chapter, the hydrologic cycle, the water cycle. So we all know what water is. I hope you know what water is. Water is a very unique element, right? It's hydrogen, oxygen, has some unique properties. It's one of the only elements, one of the only things that when it goes from water, a liquid to a solid, when it freezes, it becomes less dense. So what that means is this. If you take water and freeze it into ice, the ice floats because it actually weighs less than the water does as a liquid. If you were to melt rock and then put a solid rock in it, the solid rock would sink. So that's important because what happens is if ice acted the same way, anytime water froze like in the oceans, instead of being icebergs, it would sink to the bottom. It would stay at the bottom of the ocean where it's extremely cold. It would never melt. And basically, we would have the oceans at the top of the world and the bottom of the world frozen solid. Another thing that we talked about last chapter is that water has a very high specific heat. So it takes a lot of energy to change its temperature, and it holds a lot of energy as well. Water is often known as the universal solvent in that it really will dissolve most anything given enough time, such as dirt, rocks, different chemicals, and will move them around. And then the last one is cohesion. Water likes to stick to itself. You ever seen raindrops on the hood of a car? You got all these little drops, right? And if you push them together, they kind of stick. So water likes to stick to itself. We're going to talk about all these later on and how they interact. But let's start with some other things. The state change. So water, we know matter exists in 3 states. Liquid, solid, gas. I'm not going to get into plasma. That's a whole other thing. Let's just stick with the basic 3. Water moves through these changes. Water goes from a solid, liquid, or gas when energy is either added or removed. Right? So remember, matter is the building of everything. Everything is made of matter, and energy causes matter to change or move. And in water, it's this idea of the hydrogen bond that basically tells you whether water is solid, liquid, or gas, how well it's bonded. Let me show you what I mean. Water is made up of 1 atom of oxygen and 2 atoms of hydrogen. Now, I'm not going to go into the basic physics of this, but atoms have an electrical charge. And so an oxygen atom tends to be positively charged at this end, which means that the other end here, with a hydrogen, is positive. Positives and negatives always repel each other. So when you have any 2 molecules of water, if they come into contact, they're going to stick like this. The positive end here wants to stick to the negative, just like a magnet. And because of the shape of water, when water forms a hydrogen bond, it forms it in 30-degree angles, which is a hexagon. Water always forms a hexagon hydrogen bond. If the hydrogen bond is very strong, they're stuck together very well, that's when water is solid. It's ice. Basically, the water molecules are locked in that pattern of hexagons. And as we'll talk about later, this pattern right here is why snowflakes have 6 sides, just like water hydrogen bonded has 6 sides. Now, if we add energy in the form of temperature, we increase the movement of these molecules. They start moving together and they start to break some of the bonds. Not all of them. So maybe this one breaks this bond and this bond, but not that one, right? It's bound to 3 or 2 other ones. Now you have water. So water is just a little less stable. If you continue to add energy and increase the vibration of these molecules, the bonds break completely, and that's when water turns into a gas or a water vapor. But it is that hydrogen bond that leads to cohesion and adhesion. So water molecules naturally want to stick to themselves. They want to cohere. So let's go back to that image. This is a water molecule. If it finds another one, it's going to want to stick. It's going to have a positive side. It's going to find that negative side, and just like magnets, they're going to want to clink together and stay stuck, right? Lacking any energy, they will stay stuck. Now, the other thing is, you look at these bonds, right? So this is stuck to here. The other side of the atom here that isn't stuck still has a slight charge. So it might have a slight negative or a slight positive charge. In other words, it makes it sticky to other things, and so that's why water adheres. If you've ever put your hand in a bucket of water and you pull it out, the water runs off and drips, it's actually adhering to you and just slowly dripping off. If you've ever seen water run down a window pane when it rains and it runs down the glass, right? It's adhering, it's sticking to that a little bit. So these are some very difficult scientific terms. This describes the state changes. When water goes from a liquid to a gas, that is called evaporation. I'm being sarcastic. Hopefully we figured out that most of you know this. If water goes from a gas to a liquid, it's said to condensate. And if it goes from a liquid or solid and falls to the ground, that's precipitation. So when water evaporates, it goes into a gaseous form. When it turns from a gas to a liquid, right, it's condensation. We know what freezing is. And precipitation is any type of water, solid or liquid, that falls from the sky. Before I end, there is one other step we do see once in a while where water skips a step. Normally, water goes from a solid, it melts into liquid, and then it evaporates into a gas. So it's kind of a three-step process. Conversely, a gas may condensate, turn into a liquid, and then freeze. Once in a great while, you may see a solid go directly from a solid to a gas, and that's called sublimation. Something happens, so much energy is added right away that the water goes right away. Same thing, you might see a gas, water vapor turn directly into a solid. That can often be something, a type of frost we'll talk about. We're not going to talk about this too much. You should know that it occurs, but it's not going to be something we're going to cover too much. I'm going to pause right here, probably go get a glass of water, and then we'll start back in just a little bit.